So, Samuel, you're saying we've moved beyond just learning value functions?
Exactly. We've explored how to figure out the best actions directly.
Directly? How does that work?
Policy-based methods do just that. They parameterize the policy, like adjusting knobs on a machine to make it perform better.
Parameterize? Can you give me an example?
Think of controlling a robot arm. We'd adjust parameters, like the speed and angles, to make it pick up objects.
Interesting. And these actor-critic methods, what are they?
They're a mix. They learn both policies and value functions at once.
So, they're like using two different strategies?
Yeah, one acts, the policy, and the other judges, the value function. The actor learns what to do, and the critic evaluates how well it's doing.
Why is that better?
Oftentimes, actor-critic methods perform better in complex tasks. It's like having both a skilled pilot, actor, and a seasoned flight engineer, critic.
You mentioned deep reinforcement learning. Why is this important?
It's a whole new level of problem solving. This lets us tackle really challenging tasks, like complex games or robotic control.
So, policy-based, value-based, and actor-critic, are they all trying to find the best path?
Yes, but in different ways. It's like choosing the right tool for the job.
And actor-critic methods are, overall, the strongest approach?
In many deep reinforcement learning benchmarks, yes. They seem to combine the best of both worlds. But it depends. There might be specific scenarios where another approach is better.
So, Samuel, you're talking about policy-based methods. Can you give us a quick overview? What are they all about?
Yeah, policy-based methods are all about learning how to make decisions in a system. Think of it like teaching an AI how to play a game, or control a robot.
Right, like chess or something.
Exactly. Instead of just defining a specific set of rules, we let the AI figure out the best moves itself, through trial and error.
So it learns by doing? Sounds pretty cool. How does this differ from other ways of teaching AI?
Well, with other methods, like supervised learning, you give the AI tons of examples of what to do. With policy-based learning, we focus on the outcome, and let the AI discover the best strategies.
That's fascinating. So what are the advantages?
Policy-based methods are really good at finding optimal strategies in complex situations, where lots of factors are intertwined. And they're great for situations with lots of possible actions.
Okay, but are there downsides? Maybe it gets too complex to monitor?
It can get complex to monitor. It's an iterative process where the AI explores different actions and evaluates their success to optimize its own policy. And it can sometimes be slower than other methods.
So you're saying it explores different choices and learns from the outcome?
Precisely. And the algorithm you mentioned, reinforce, is a simple policy gradient method. It adjusts its strategy based on the outcome of those actions.
And how does it work exactly?
Reinforce uses gradients to determine how much to change the AI's strategy. Basically, it helps the AI decide which decisions lead to better results and modifies the policy accordingly.
Interesting. So, in essence, it's like a feedback loop, right?
Absolutely. It's about refining the AI's decision-making strategy based on its experience.
Makes sense, a kind of trial and error learning. So, where might we see reinforce in practice?
You'll see it in robotics, game playing, even in finance, where algorithms need to make complex decisions in response to market changes.
So, Samuel, you're saying policy gradient methods are superior in some situations? How do they handle continuous action spaces?
Yeah, absolutely. Value-based methods struggle with high-dimensional or continuous action spaces. Imagine trying to find the best action in a game with infinite possibilities. Computationally, it's very hard.
Right. So, policy-based methods provide a different approach. Tell me more about that.
They learn a policy function that maps states to probabilities of actions. This makes learning in continuous spaces much easier.
And how does this relate to partially observable environments?
Well, if you can't fully understand the environment, a stochastic policy, a policy that chooses actions with probabilities, is often better. It's more flexible.
So, less reliance on the Markov assumption?
Exactly. The Markov assumption says the current state totally determines the next state. But in a lot of real-world problems, that's not always true. You know, maybe a single observation isn't enough.
A great example then is learning to play a game with imperfect information like poker, right?
Precisely. In those situations, randomly choosing actions with specific probabilities, that's where stochastic policies excel.
So, if an agent can't fully determine a state, acting randomly is the best strategy?
Not exactly random in the sense of truly random. It's about strategically acting with probabilities, giving the agent flexibility. Think of it like a mixed strategy in game theory.
Makes sense. So, policies can be learned in more flexible ways. Thanks, Samuel.
My pleasure.
So, Samuel, you're saying learning policies directly might be easier than value functions? Intriguing. Can you elaborate on that a bit?
Yeah, absolutely. Imagine a super long hallway. Lots of cells. 2 exits. The optimal path, well, it's pretty obvious. But figuring out the values of each cell? A lot of extra work.
Makes sense. Why is the policy approach potentially easier in this scenario?
Because we're focusing on the action probabilities. Instead of calculating precise values, we're finding the best actions at each point. Finding the most direct way towards the nearest goal.
So, you're saying the approach prioritizes actions, not values, in this simple hallway example?
Exactly. We don't need to know the precise value of each cell to know a left turn is better than a random one. You know?
Right. Makes sense. So you're implying that calculating the ideal action at each cell can be more straightforward than finding the entire value function.
Absolutely. And that's a key advantage in learning these policies. Less data needed often.
Okay, let's dig into the code snippet. This FCDAP class, what's it about?
It defines a stochastic policy for discrete actions. It's essentially a neural network designed to learn probabilities of actions given a state. Think of it as a decision-making engine, learning what actions are best in different situations. Each state has different actions to take.
So, this network maps states to action probabilities.
Precisely. It takes a state, computes probabilities for each possible action, and then selects a random action based on these probabilities.
What about convergence? Why is this approach better?
Well, policy-based methods tend to converge better. Changes in the policy are smooth, gradual adjustments. Value-based methods, can oscillate. Small changes in value can cause big jumps in action. Kind of like, a tiny nudge can send you wildly off course. Not good for stability. A smoother, more controlled change is key.
So, the FCDAP class, through its architecture, basically steers away from sudden changes?
Exactly. It ensures smoother, more predictable policy updates. This results in better convergence.
How does the code actually sample an action given a state?
It takes the state, feeds it to the network, receives action preferences, transforms these preferences into a probability distribution, and then samples a random action based on that distribution.
So, the network calculates probabilities for all possible actions?
Yes. And it chooses a random action from this distribution, ensuring some exploration rather than always going for the immediately most probable action.
Excellent. So, this FCDAP class makes learning policies smoother and potentially faster than alternative approaches. So, you're saying we can directly optimize policies without needing value functions? That seems counterintuitive.
Yeah, it is a bit mind-bending at first. But think of it this way, we're directly aiming for the best actions instead of figuring out the best overall outcome first.
Okay, so you're skipping the intermediate step of defining the value function. Can you explain how that works?
Sure. We're focusing on the probability of trajectories, the whole sequence of states, actions, rewards.
Trajectories? Like a complete path?
Exactly. We look at the likelihood of the whole journey, and by changing the policy, we directly alter the trajectory's probability.
So, how do we measure this probability?
We use a series of probabilities. The probability of the initial state, the probability of the action given the state, the probability of the next state and reward given the previous state and action, and so on all the way down the line. It's a product of probabilities at every step.
So, we're multiplying all these probabilities together to get the total probability for that full trajectory. That's a lot of calculations.
Yes, but the key here is taking the log of that probability. Turning the product into a sum. makes the calculations a lot more manageable.
And why take the log?
That's a crucial mathematical trick. Differentiation becomes easier. We can find the gradient, which tells us how to tweak the policy to improve the objective, which is the expected return of the entire trajectory.
So, you are essentially updating the policy based on the likelihood of a trajectory's occurrence.
That's right. And remember, the objective function is now just the expected value of the sum of the log probabilities of all those trajectories.
So, the gradient of this new objective function is dependent on the policy alone. No intermediate value functions required. How does that directly connect to a better policy?
Because the gradient tells us the direction in which the policy needs to change to increase the expected return. We can update the policy in that direction using a gradient-based optimization algorithm.
This seems powerful. What are some practical applications?
Imagine training a robot to navigate a complex environment. Instead of first defining a value function, we directly learn the robot's actions to maximize its success rate.
So, we're talking about variance and policy gradients, right? Reinforce, powerful, but volatile.
Precisely. High variance makes it tricky to interpret results. Think about it like aiming a dart at a target. Reinforce is like taking a bunch of shots, and the average might be close, but the spread's huge.
And the randomness comes from the trajectory, right? The actions, states, and rewards all have a random element?
Exactly. The compounding of all that randomness makes interpreting the signal hard. It's like adding noise to a noisy signal.
Okay, so partial returns are one way to tame the variance? We've already touched on that.
Right. Using a shorter partial return gives us a less noisy signal. But even with that, the log probabilities of actions are still directly tied to the return.
So, a huge reward makes those actions way more likely?
Yeah, a big positive reward dramatically boosts the probabilities. Conversely, a big negative reward drastically lowers them.
That sounds unstable. And in environments like cartpole, where everything's positive.
You hit the nail on the head. If all rewards are positive, getting that data to differentiate good actions from great actions becomes incredibly hard. The variance is tough to control.
So, what's the solution? A way to look at action values within the same state, regardless of the total return?
Yep. That's where advantage functions come in. We can estimate the advantage of taking a specific action in a particular state.
How does this work? Explain the advantage function.
The advantage function, basically, tells us how much better or worse an action is compared to the average action in a given state. We take the return from that state and subtract the average expected return in the same state.
Wait, so it's a comparison within that state?
Exactly. Instead of relying on the noisy return for all past interactions, we estimate the benefit of a single action directly. That reduces the variance in a state significantly. This is a critical step toward stabilizing and improving the reliability of policy gradient methods.
So, it's like focusing on the local rewards within the state. Clever.
Yeah, really clever. It helps to distinguish between good and great actions in the same state. It makes our policy learning much more efficient.
Makes a lot of sense. Thanks, Samuel. Okay, Samuel, so we've been talking about VPG. Now you're mentioning A3C. What's the big difference?
Well, VPG, while pretty good, can have some variance issues.
Variance issues? Can you explain?
Yeah, so imagine trying to hit a target. VPG's like aiming with a pretty steady hand, but sometimes the target moves a little. It's relatively accurate, but there's still a bit of wiggle room.
Got it. An A3C?
A 3C is like using a laser pointer with multiple assistants. It uses multiple actors working in parallel.
Multiple actors? That's interesting. So you're essentially getting multiple attempts at hitting the target?
Exactly. And those multiple attempts, well, they help narrow down that wiggle room. It also uses a technique called n-step returns with bootstrapping. Think of it as taking the average of multiple shots instead of just one.
So more data points? That makes sense. More data should reduce the variance.
Absolutely. It's like having a much more precise aim. By using multiple actors and n-step returns, A3C reduces the variance significantly.
And is that trade-off with more bias?
Well, VPG is pretty unbiased, but in A3C, using bootstrapping introduces a slight bias. It's a calculated trade-off. Less variance often comes at the cost of a little bias. But it can be worth it.
That makes perfect sense. So you're gaining stability at the expense of some precision?
Exactly. It's an engineering compromise. A 3C is generally more stable, but you've got to consider if that stability outweighs the potential loss of accuracy in the learning process. In situations where speed is critical, like complex game scenarios, a 3C might be the better choice.
Makes sense. Thanks, Samuel. So, Samuel, you're saying that using multiple workers for on-policy methods like policy gradients helps with variance?
Yeah, Alfred. It's a crucial difference. Traditional replay buffers, used for off-policy, work well because they create a dataset of experiences that are somewhat independent.
Independent? Like, each experience doesn't affect the next?
Precisely. But in on-policy methods, every training step relies on recent data. That creates correlations.
So, multiple workers help break those correlations?
Exactly. Each worker explores the environment independently, generating new experiences. These independent experiences, when combined, reduce the impact of those correlations. Think of it like running multiple experiments, each one distinct, but all contributing to the overall picture.
Makes sense. So, it's like a more dynamic way of gathering data?
Exactly. Instead of just sampling from a fixed dataset, it's a live, evolving dataset.
But, how does that affect the value function?
The value function, which estimates the future reward, gets updated concurrently. It's updated as the experiences come in, reflecting the current policy.
So, the policy and the value functions are adjusting in real time, based on the experience of multiple workers?
That's right. The parallel nature of the workers really speeds up learning, and it avoids the limitations of sampling from a fixed, potentially outdated replay buffer in on-policy learning.
Fascinating. And are there any potential drawbacks or gotchas with this approach?
Absolutely. Synchronizing multiple workers can be tricky. Imagine these workers constantly pushing data, and if the system isn't well designed, you could have data conflicts or inconsistencies. Proper synchronization strategies are vital.
That's an important point. So, this asynchronous nature, while powerful, demands careful engineering?
Exactly. Proper error handling and queuing systems are needed to ensure data consistency. And the update frequency becomes important too. Too fast, and you're overfitting on noise. Too slow, and the learning will be less efficient.
So, we're trading off the benefits of independence with the complexities of synchronization. What's the overall takeaway?
On-policy methods with multiple workers are a powerful approach for reducing variance and potentially speeding up learning, but you need to be thoughtful about how to implement it efficiently. It's about striking the right balance between speed and precision.
Okay, Samuel, so we're talking about A3C now. This hog-wild approach, it sounds pretty radical. Why ditch the locks?
Yeah, it's a bold choice. Imagine a bunch of workers updating a shared model. Locking creates bottlenecks, right? Everything has to wait its turn. Hogwild says, let 'em rip. Updates happen concurrently, but there's a clever way to manage potential conflicts.
So, a race condition? How does that not mess things up?
Exactly. That's the key. We're not trying to avoid race conditions entirely. Instead, we let the updates happen asynchronously. A 3C's update method minimizes the risk by averaging out the different results, sort of like a moving average that smooths out the noise.
Interesting. Can you elaborate on the practical implications of this approach?
Absolutely. Imagine training a really complex game-playing AI. With locks, you'd have huge delays in training. Hogwild speeds up things considerably. You see a huge gain in training speed.
What about the shared atom optimizer? That sounds like a crucial part.
It is. We need a way for the workers to share the optimizer's internal state. Normally, these variables would be local to each process. But we need them in shared memory.
So, this shared memory method, how does it work?
Right. The shared atom class cleverly handles this. It copies the atom optimizer variables to a shared memory area, so all the workers can access and modify those variables concurrently.
What about the step function? What's its significance?
Crucially, the step function is overridden. It keeps track of steps for each parameter during the update, which are then used in the update process, guaranteeing a smooth and correct update.
So, we're essentially letting the workers update the model simultaneously. But how do we prevent total chaos?
The Hogwild method does a clever averaging at the end, ensuring that the final model update reflects a combination of the workers' changes. We're still managing that chaos, but in a much more efficient way.
So, it's all about optimizing the speed of training deep reinforcement learning models?
Yes, absolutely. This combination of Hogwild updates and shared optimizers is a powerful tool for accelerating the training of large, complex RL models and is very effective.
That's a really interesting concept. Thanks, Samuel. So, Samuel, you're talking about weight sharing in actor-critic networks. Why is that beneficial, especially with image data?
Yeah, weight sharing, it's a neat trick. Imagine you're training a network to play a game. You need a policy to decide what action to take, and a value function to estimate how good that action is. With weight sharing, you use the same neural network for both.
That seems counterintuitive. Wouldn't the different goals of the policy and value function create problems?
Potentially, but in image-based tasks, where extracting features is costly, weight sharing can be a real boon. You're reusing those learned features, making the whole thing more efficient.
Interesting. Can you elaborate on how the weights are shared, specifically?
It's not just sharing all the weights. The network structure, similar to a dueling network, has two output layers. One's for the value output, and one for the policy output. Both of these connect to the last layer of your shared hidden layers. That's key. It lets you reuse the learned image representations.
So, you're saying you're utilizing the same learned features from the image in determining both policy and value.
Exactly. You don't have to build two separate feature extraction pathways. Think of it like a shared knowledge base.
Okay, so let's look at the code. We see a FCAT class. What's its purpose?
That's the fully connected actor-critic model. The __init___ function sets up the network. It takes input dimensions, output dimensions, and hidden layers sizes. It's essentially defining your network architecture. You'll recognize the familiar pattern: an input layer, hidden layers, and output layers. Crucially, these layers are shared.
And the forward function?
The forward function takes your input state, converts it to a tensor if it isn't already, reshapes it as needed, then feeds it through the network layers, including the activation function, layer by layer, ultimately outputting both the policy logits and value.
So, in essence, the same computational path creates both the policy and the value estimations.
Precisely. It's like having one brain work for two distinct purposes, but leveraging the same fundamental understanding.
So, there are potential complications due to scales of policy and value updates.
Correct, which is why this isn't always the best choice. In some situations, separate networks can lead to faster learning because they adapt independently to their respective objectives. You have to look at the trade-offs.
Right, so weight sharing is a powerful tool, but it's crucial to understand its trade-offs.
Absolutely. It's about finding the optimal strategy for your specific problem.
So, Samuel, we've covered value-based methods. Now you're talking about policy gradient and actor-critic. What's the big difference and why do we need them?
Yeah, policy-based methods, like policy gradients and actor-critics, aim to directly learn the policy. Instead of learning values, they learn the best actions to take in different situations. This can be really helpful in complex environments where value-based methods might struggle.
Like, what kind of environments?
Environments with lots of uncertainty or partial observability. Imagine a robot navigating a cluttered room. Knowing the value of a state doesn't directly tell you the best path. Learning the policy, what moves to make, is crucial there. Plus, these methods can often yield better performance than value-based methods.
So reinforce sounds like a basic policy gradient method. Tell me more.
Reinforce is pretty straightforward. It just adjusts the policy based on the total reward received. It's like trial and error, but with a more intelligent approach using gradients. We can also use the reward to go, the accumulated reward from the current step onward, to refine the policy even better.
And the vanilla policy gradient? What's the tweak there?
That's reinforce with a baseline. We learn a value function to estimate the expected return, and then use this value as a baseline to make updates to our policy. It reduces variance, which is a huge problem in policy gradients, leading to more stable learning. It's a smoother ride to better performance.
A 3C, is that using a different approach?
A 3C leverages multiple agents learning in parallel, working together on the same policy, and bootstrapping for better value function estimations. It's kind of like having lots of little robots all practicing in a simulated environment, and they all learn from each other pretty quickly. They update the model in a lock-free way, so they don't get stuck waiting.
You mentioned bootstrapping. Why is that better?
Bootstrapping estimates the value function based on past results, which smooths out the learning process. It uses the estimated value function to make adjustments, which is more efficient than relying only on the immediate reward. It's a bit like leveraging experience.
In GA, I see that's sort of a mix of different approaches.
Exactly. GA combines the advantages of using multiple returns like n-step returns with the benefits of TDA. It blends different ways of looking at expected future rewards to create a much more robust estimate for our algorithm, balancing bias and variance in a flexible way. It lets us adjust how much bootstrapping to use, giving us a lot of control.
Finally, a 2C, a simpler version?
A 2C takes A3C and removes the parallel learning. You get a much more straightforward algorithm without the complex asynchronous nature of A3C. That means you can train it with standard optimization rather than needing custom code. It's a simpler, but still very effective option.
So, we've learned about the various methods here. What would you say is the best approach for a particular task?
That really depends on the environment and your priorities. For complex, partially observable environments with a need for speed, a 3C might be best. A 2C might be a better option for cases with resource constraints. For a more versatile approach, GAE is quite flexible, allowing us to control the trade-off between using more immediate returns and extrapolating future returns to refine a well-rounded approach.